Okay, on the previous video, we had just finished our increasing, decreasing. So now that I see where we're increasing and decreasing, I can talk about my local extremes. And so at x equal -2, with y equal f of -2, and remember, when you're finding y coordinates, it's always the original function. And so you can just trust me here, when we plug into the original function, you are going to get, and that's going to give me a couple moments to get my original function in here. When I plug into my original function, and I'll go through those key sequences one more time and making my calculator do it. So I've put into y1 the original function, x squared e to the x, into y1. Then I go back to the home screen, so I'll quit that. Then you can hit vars, if your calculator will work with you. My calculator's not working with me. Vars. Let's try one more time. My calculator is apparently dead. Clear. Okay, so my calculator doesn't want to do this for me. We are screwed. Let's see. There, y vars. So you hit vars, arrow over to y vars, then it's a function, so I press 1, then press 1 again because I put it into y1, then you put the number that you want, so y1 of -2. Enter, and I get 0.54. And so f of -2 is 0.54. And so I have -2, 0.54, and that is going to be a local maximum because I go from increasing to decreasing, or my first derivative changes from positive to negative, and so we had to hit a max. Okay, what I've told you about don't give me decimals unless I give you decimals. We are graphing here. Graphs are estimates at best. Now, yes, the actual point here would be 4e to the -2. 4e to the -2 is hard to graph. 0.54, not hard to graph. So since we're doing graphing, decimals okay. Doing the same thing at 0, at x equals 0, with y equal f of 0. And I can even do that one by hand. That would be 0. Gives me 0, 0. And at 0, it changes from decreasing to increasing. Or the first derivative changes from negative to positive. And so that means it's a local minimum. And there's all my increasing, decreasing work. So now we're going to go on to concavity work. Concavity stuff. We use the second derivative, which we were given that the second derivative was 2e to the x plus 4x e to the x plus x squared e to the x. So I find my possible inflection points. I set that second derivative equal to 0 and solve. We can start by factoring out that e to the x. And go up here and finish. That is factored and equal to 0, so I can split that up. We already know, we've seen this before, this has no solution. And again, that doesn't mean anything, just they're not getting a possible inflection point here. Here you can look around at that as long as you want, it's never going to factor. So using the quadratic formula, which we'll do on the next piece of paper, It's very hard to find a problem that has nice numbers all the way through it. So don't be surprised if you have to go to something like the quadratic formula. And so we're going to have x equals -4 plus or minus 4 squared minus 4 times 1 times 2 over 2 times 1. So it's -4 plus or minus 16 minus 8 over 2, which is -4 plus or minus the square root of 8 over 2, which is -4 plus or minus, simplifying that radical, square root of 8 is 4 times 2, -4 plus or minus 2 square root of 2 over 2. And notice now I'm going to divide everybody by 2. And so when I divide everybody by 2, so I'm dividing by 2 there. So I get -2 plus or minus square root of 2. And so there are my possible inflection points. And again, because we're graphing, and none of us want to graph those numbers, because we're graphing, get some decimal equivalence here. -2 minus the square root of 2 is approximately equal to -3.41. -2 plus the square root of 2 is approximately equal to -0.58. So now making my concavity chart. Those are possible inflection points until I make the chart and see the change in concavity. So it's going to be -infinity to -2 minus the square root of 2, -2 minus the square root of 2, to -2 plus the square root of 2, -2 plus square root of 2, to infinity. Then this guy here was a roughly -3.41. This guy here was roughly -0.58. Test value. How about -4, -1, and 0? And then I plug into my second derivative. And let's recall, I'll write it down here. My second derivative. Give myself a little more space there. Actually, we'll write it up here. The second derivative was 2e to the x. And I'm going to give it in the factored version. It was e to the x times 2 plus 4x plus x squared. That's what was my second derivative. So now when I go and I have to plug into my second derivative, again, you have some choices here. You could take your -4 and plug it into the whole thing there and see what value you get. Or you can go with the factored form, this is factored, and just do each part. Well, now here's the interesting thing. That's what we're going to do. We're just going to do each part and analyze what's going on. E to the 4x is always positive. E to any exponent is always positive. So the sign of this entire expression is really coming from the 2 plus 4x plus x squared. This is e to the x is always positive, so this is really what's determining the sign. So I can just plug -4 into that parabola there and see what's going on. So if I plug -4 into there, that's going to be 16 minus 16 plus 2, and that's going to be positive. If I plug -1 into here, and kind of going backwards, if I plug -1 into here, that's going to be 1 minus 4 plus 2, 1 minus 4 plus 2, that's going to be negative. And finally plug 0 in here, 0 plus 0 plus 2, that's going to be positive. And again, if you can't analyze it like that, you can take that number, plug it into the whole second derivative, see what you get. Just be careful of your calculations. And so this tells me that f of x is concave up, down, and up. Positive second derivative means we're concave up. Negative second derivative means concave down. I see actual changes of concavity, so I have inflection points at, and we'll go with the decimals because we're about to graph. So x equal negative 3.41 with y equal f of negative 3.41. Always the original function. Y coordinates always come from the original function. So if I put negative 3.41 in there, and you can trust me on this one hopefully, we get 0.38, squiggly equal mark approximately equal to. So we have negative 3.41, 0.38 as one inflection point, and at x equal negative 0.58 with y equal f of negative 0.58. Again, the original function. If I put negative 0.58 in there, we come up with roughly 0.19. And so negative 0.58, 0.19 is my other inflection point. And now we're ready to sketch. So I'm going to go on to another piece of paper and write down what we found as far as points. We found that we had a local max of negative 2.54. We found that we had a local min of 0, 0. And we had inflection points of negative 3.41, 0.38, and negative 0.58, 0.19. And now we are going to think before we draw. The important x values that we got. Were this, from smallest to largest, negative 3.41, negative 2, negative 0.58, and 0. The important y values we got were x equal 0, 0.19, 0.38, 0.54. And the reason why I list them is I'm going to think very carefully about my axes. I'm going to think what I want my axes to be before I draw it. Then I'm going to make very careful considerations here, which I will do on the next video.